In this video, we're going to look at why we can use electrolysis to extract metals and when we would use it to extract metals. We're then going to look at why we can't extract aluminium directly from its ore using electrolysis. We'll then cover the process for extracting aluminium by electrolysis, and we'll explain why the electrodes involved in this process need replacing. Finally, if you're doing the higher tier, we'll write half equations for this process. So earlier in this topic, we looked at how we can extract metals using carbon. We're going to quickly recap that process. So a metal which is below carbon in the reactivity series, so zinc and all the metals underneath that, can be extracted from their ores by reacting it with carbon. Remember, a metal ore is a rock which contains enough of the metal in that rock to make it profitable to extract the metal. So for example, if we looked at iron, that's underneath carbon in the reactivity series. Iron ore is found as iron oxide. So if we react the iron oxide with the carbon, we get iron and we make carbon dioxide. So this is how the metal is extracted by using carbon. However, if a metal is above carbon in the reactivity series, this means the metal is more reactive than carbon. These metals can't be extracted from their ores by reacting with carbon. Since carbon is less reactive than these metals, it can't take the oxygen from those metal ores to form carbon dioxide, so no reaction will happen. We're looking at how we can extract aluminium from its metal ore. We can see that aluminium is above carbon in the reactivity series, so we can't use extraction by carbon. We're going to have to use electrolysis instead. Aluminium is found in an ore called bauxite. This bauxite ore can then be mined and purified to produce aluminium oxide. However, we can't use aluminium oxide in electrolysis. Aluminium oxide has a melting point of around 2000 degrees. This means it would require way too much energy to be economical to melt for the process of electrolysis. If you're a company looking to extract the aluminium from the aluminium oxide, you'd probably spend more money heating up the aluminium to melt it than you would from selling the aluminium, so it's not worth extracting it this way. Instead, we dissolve the aluminium oxide in molten cryolite. This lowers the melting point of the aluminium oxide to about 900 degrees. And with a melting point of around 900 degrees, it is economical to pay for the energy to heat it up, to melt it, to extract it with electrolysis. This is a simplified diagram of the equipment used to extract aluminium through electrolysis. You'll notice that this looks different to the electrolysis setup we've looked at in previous videos. We're going to work through each part of the diagram. The first thing to note is that we have lots of positive electrodes. We'll come to where the negative electrodes are in a second. So unlike the small-scale electrolysis we've looked at so far, the electrolysis of aluminium takes place in a very large reaction vessel. The electrodes are made out of graphite, which is just a form of carbon. That's important for later on. Now, when we're extracting aluminium, the rest of the vessel is the negative electrode. So all the walls of the reaction vessel are connected up to an electric power lead, and they are the negative electrode. So as opposed to having a negative electrode like we've looked at before, the entire outside, so the entire surroundings of the vessel are the negative electrodes. And this is also made out of graphite. And then our electrolyte is this molten cryolite, which contains aluminium ions and oxygen ions. So the positive aluminium ions are attracted to the negative electrode, which is the walls of the container. They'll form aluminium metal on the walls of the container, fall to the bottom, where they're then siphoned off and collected. The oxygen ions are negative, so they will move to the positive electrode. Now, it will form oxygen gas at the positive electrode. However, we've said that the electrodes are made out of carbon, so another reaction happens at these electrodes. The oxygen we've formed reacts with the carbon to form carbon dioxide gas. Now, this is wearing away the electrodes. Those electrodes are made out of carbon, so every time the oxygen reacts with the carbon to form carbon dioxide, it's eating away at the electrode. There's less and less of it left. Therefore, the positive electrodes are worn away over time and need to be continually replaced during this process. We're now going to look at the half equations for this process. First, we'll look at the overall equation. So the aluminium oxide decomposes into aluminium and oxygen. However, this equation isn't balanced, so the first thing you need to do is balance it. You can now see that we've got a balanced equation. We've got 4 aluminiums on the left and the right, and 6 oxygens on the left and the right. We'll now look at the half equations for each of the elements, the aluminium and the oxygen, separately. We'll start off with the aluminium. So we know the aluminium is a metal. It will form a positive ion. Therefore, this reaction happens at the cathode, which is the negative electrode. We know from looking at the periodic table that aluminium is in group 3, therefore it'll have a 3 positive charge. So this is the process we're going through. Aluminium with a 3 plus charge to aluminium metal. This means we need to add 3 electrons to the aluminium, so reduction is happening, it's gaining electrons, to write this half equation. If you're unsure on how we've written this half equation, look back at the half equation video and we go through how to do this process in a lot more detail. The oxygen will form a non-metal ion, so its reaction will take place at the anode. We know oxygen is in group 6, it'll have a 2 minus charge, so we're going from O2 minus to O2. We balance the half equation, so we've got 2 oxygens on each side, and then add the electrons to complete the equation. Again, watch the half equations video if you're unsure on how we've written these.